Section: Introduction. In this section, we will discuss how diffusion models, DMs, have transformed computer vision research by excelling in text-guided content generation tasks like image editing and video generation. Despite their high performance, DMs require significant computational resources. Latent diffusion models, LDMs, have made text-to-image generation more accessible, but they are still slow. To tackle this issue, different approaches for efficient DMs have been introduced, focusing on sampling strategies and model architecture. Efficient sampling methods can reduce denoising steps but do not address memory and compute costs. On the other hand, efficient architectures can lower the cost of each step and be combined with sampling strategies for better efficiency. However, most existing efficient architecture methods need retraining, which is time-consuming and costly. To address these challenges, we introduce the Attention-Driven Training Free Efficient Diffusion Model, AT-EDM, framework, which speeds up DM inference without retraining. We focus on accelerating pre-trained DMs by leveraging attention maps. Our approach involves token pruning for denoising steps, using a graph-based algorithm called Generalized Weighted Page Rank, GWPR, to identify unnecessary tokens in attention maps. We also introduce a novel token recovery method to maintain image quality. Additionally, we analyze attention map variances across denoising steps and propose a pruning schedule called Denoising Steps Aware Pruning, DSAP, to adjust pruning ratios, improving both our method and other runtime pruning approaches. Our contributions include the AT-EDM framework, a token pruning algorithm, the GWPR algorithm for identifying redundant tokens, a token recovery method, and the DSAP schedule for enhancing generation quality. By applying AT-EDM to the SDXL model, we achieve state-of-the-art results with a significant reduction in computational costs. Our method outperforms existing approaches by generating clearer images with sharper details and better text-image alignment. Section Summary. In this section, we introduce diffusion models, DMs, which have significantly advanced computer vision tasks but are computationally expensive. To address this, we propose the Attention-Driven Training Free Efficient Diffusion Model, AT-EDM, framework, which accelerates DM inference without retraining by dynamically pruning redundant tokens using the Generalized Weighted Page Rank, GWPR, algorithm. Additionally, we develop a Denoising Steps Aware Pruning, DSAP, schedule that adjusts pruning ratios across denoising steps, improving image quality and outperforming existing methods like token merging, TOME, in terms of generating clearer objects with sharper details and better text-image alignment under the same acceleration ratio. Section: Methodology. In this section, we begin our investigation by examining the computational operations, FLOPs, of the Advanced DM Model, SDXL. We observe that within the sampling module, UNet, attention blocks, which are made up of multiple attention layers in a row, are the main contributors to the workload for generating images. To address this, we introduce AT-EDM, a method to speed up attention blocks in the model through token pruning. AT-EDM consists of two key components: a token pruning scheme in a single denoising step and the DSAP schedule. We will provide an overview of these components and then delve into a detailed discussion. In the first part, which is the token pruning scheme in a single denoising step, we follow these steps. First, we extract the attention maps from an attention layer in the UNet, which can be from self-attention or cross-attention. Next, we use a scoring module to assign importance values to each token based on the attention map. We employ the GWPR algorithm for this task. Then, we create pruning masks based on the calculated importance distribution, where we retain tokens with higher importance and prune those with lower importance. After that, we apply the generated mask to perform token pruning, either after or before the feed-forward layer of attention layers. This process is repeated for each consecutive attention layer, except for the last one before the ResNet layer. Finally, before passing the pruned feature map to the ResNet block, we need to fill in the pruned tokens. We achieve this by copying tokens to corresponding locations based on their similarity. Moving on to the DSAP schedule, we notice that attention maps in early denoising steps are less informative and more chaotic compared to later steps. Therefore, we design the DSAP schedule to prune fewer tokens in the early denoising steps. This involves selecting specific attention blocks in the upsampling and downsampling stages to leave unpruned, as they contribute significantly to the quality of the generated images. In the token pruning process, we define the attention map as an adjacency matrix of a directed graph. We use the GWPR algorithm to assign importance values to key and query tokens iteratively. For self-attention, query tokens are the same as key tokens, while for cross-attention, we map importance values from key to query tokens using a specific function. We also discuss methods for recovering pruned tokens, such as padding zeros, interpolation, and a similarity-based copy technique. Section Summary. In this section, we propose AT-EDM to accelerate attention blocks in the model through token pruning, consisting of a single denoising step token pruning scheme and the DSAP schedule. The token pruning scheme involves obtaining attention maps, assigning importance to tokens using the GWPR algorithm, generating pruning masks, and filling pruned tokens before passing them to the ResNet block. The DSAP schedule prunes fewer tokens in early denoising steps based on the variance of attention maps, leaving some attention blocks unpruned for better image quality. Section. Part 2. Denoising steps-aware pruning. In this section, we focus on denoising steps in our model. Early denoising steps play a crucial role in shaping the generated images, while late denoising steps refine the image, sometimes redundantly. Early steps struggle to distinguish between important and unimportant parts of the image, making it challenging to prune effectively. To address this, we introduce a strategy called DSAP, which delays pruning in the early denoising steps by leaving some layers unpruned. In our DSAP approach, we choose specific attention blocks in the model to skip token pruning. We avoid pruning the first attention block in each downstage and the last attention block in each upstage. This strategy is applied for the initial denoising steps. Through experiments, we determined that setting the parameter tau to 15 is the best choice for optimal performance. We compare our DSAP approach with a more aggressive pruning schedule in the early denoising steps and find that our current strategy outperforms the aggressive one. Our experimental results on SDXL show the effectiveness of our AT-EDM method compared to TOME. We evaluate both visually and quantitatively, demonstrating the advantages of AT-EDM over TOME. For our AT-EDM method, we incorporate a pruning layer after the first attention layer of each attention block with a specific pruning ratio. To meet the computational budget, we set the pruning ratio to 63%. Additionally, we implement the DSAP strategy by not pruning certain attention blocks in the early denoising steps. In contrast, TOME requires a more aggressive merging setting due to changes in the SDXL architecture. We extend the token merging application to various layers and set the merging ratio to 50% to meet the computational budget. We evaluate the generated images using challenging prompts and report FID and clip scores on the MS-COCO 2017 validation dataset. Visual examples show that AT-EDM outperforms TOME in preserving main objects and aligning text with images. Our DSAP strategy not only benefits AT-EDM but also enhances the quality and alignment of images in TOME. By implementing DSAP in TOME, we improve image quality and text-image alignment while maintaining computational efficiency. Section Summary. Part 2. Denoising steps-aware pruning. In this section, we investigate the impact of denoising steps on image generation quality. Early denoising steps determine image layout, while late steps refine images, with early steps struggling to differentiate important and unimportant tokens. To optimize this, we propose a prune-less schedule for early denoising steps, leaving specific attention blocks unpruned, resulting in improved image quality and text-image alignment. Section. Quantitative evaluations. In this section, we examine the trade-off between clip and FID scores using different classifier-free guidance, CFG, scales. We present our findings in Fig. AT-EDM does not apply pruning at the second feature level, as detailed in the supplementary material. Our results show that AT-EDM generally reduces FID scores and improves clip scores compared to TOM. This suggests that images generated by AT-EDM not only have higher quality but also better alignment with text. Specifically, when the CFG scale is 7.0, AT-EDM achieves FID, clip, equals 28.0, 0.321, which is close to the full-size model's performance, 27.3, 0.323, at CFG scale equals 4.0. In contrast, TOM yields 35.3, 0.320, with a CFG scale of 7.0. Therefore, AT-EDM reduces the FID difference from 8.0 to 0.7. We then compare TOM and AT-EDM on SDXL under various FLOPS budgets, as shown in table. The FLOPS cost refers to the average cost of FLOPS for a denoising step. The table demonstrates that AT-EDM consistently outperforms TOM in image quality, lower FID scores, across all FLOPS budgets. Notably, when FLOPS are significantly reduced, less than 50% of the full model, TOM achieves higher clip scores than AT-EDM. However, with a 30 to 40% reduction in FLOPS, AT-EDM not only improves image quality, lower FID scores, but also enhances text-image alignment, higher clip scores, compared to TOM. Remarkably, under the same CFG scale, AT-EDM achieves lower FID scores than the full-size model while reducing FLOPS by 32.8%. Moving on to latency analysis, SDXL utilizes the fused operation, FO, library, X-formers, to enhance generation speed. The current implementation of X-formers does not provide attention maps as intermediate results, necessitating additional attention map calculations. We evaluate the sampling latency for 3 scenarios: without FO, with FO under the current implementation, C, and with FO under the desired implementation, D, that offers attention maps as intermediate results. Our analysis reveals that deploying pruning at the second feature level incurs a higher cost than the latency reduction it provides. Consequently, AT-EDM is faster than AT-EDM. Additionally, we illustrate the extra latency introduced by different pruning steps in Fig. AT-EDM achieves notable speedups of 52.7%, 15.4%, and 17.6% in latency without FO, with FO under C, and with FO under D, respectively, with minimal quality loss, surpassing existing methods significantly. In the ablation study, we compare self-attention, SAW, and cross-attention, CA, based on GWPR. Our analysis indicates that SAW-based WPR outperforms CA-based WPR due to the latter pruning excessive background tokens, making background recovery challenging. We also introduce a similarity-based copy method for filling pruned pixels, demonstrating its superiority over other methods in image quality enhancement. Furthermore, we explore different design choices for denoising steps-aware pruning, DSAP, highlighting the effectiveness of the FL, first-last, schedule and the optimal number of early prune-less steps for enhancing image quality.